You can buy a valve with the right pressure class, the right body material, the right seat design, the right actuator, and a certificate that says fire safe, and still misunderstand what that valve will actually do when fire destroys the conditions under which it normally seals. That is the uncomfortable starting point. A valve does not become invincible because a datasheet carries a fire test reference. It does not become leak-free under fire. It does not automatically protect your plant simply because the procurement document contains the right clause. What the qualification really tells you is more precise. It tells you whether a defined valve design, tested under controlled fire exposure, can limit through-seat leakage, limit external leakage, survive the heating and cooling cycle, and still perform a required movement after severe thermal damage has already begun. That is not a guarantee of perfection. It is evidence of controlled degradation, and that distinction matters. Under normal service, valves depend on resilient seats, packing systems, gaskets, contact stresses, dimensional tolerances, and pressure-assisted sealing. Fire attacks all of them at once. Soft materials may decompose. Packing may lose integrity. Clearances may change. Bolted joints may lose preload. Stem friction may rise. Seat contact may distort. Trapped liquid may expand. Body cavities may overpressure. The valve you trusted before the fire is no longer operating under the same mechanical reality. The real engineering question is not, will nothing fail? The real question is, when normal sealing starts to fail, what remains capable of containing pressure? That is the heart of fire-safe valve design. The primary sealing system gives you normal performance. The surviving metallic geometry, secondary sealing features, and pressure boundary give you emergency performance. The test exists to prove whether that fallback works. And this is where many engineering teams become dangerously casual. They see fire safe and stop thinking. They accept a certificate, they close a comment, they approve the valve. But a certificate is only meaningful when the tested valve is technically representative of the valve you are buying. You must ask what was actually tested. What size? What pressure rating? What seat material? What stem packing? What body seal? What body joint? What internal geometry? Was the design symmetric? Was it tested in both flow directions where required? Does the qualification legitimately extend to the purchased valve? Same series is not an engineering answer. Similar model is not an engineering answer. Designed on fire-safe principles is not an engineering answer. You need traceability. The qualification must connect the test article to the supplied product without gaps, assumptions, or commercial shortcuts. That includes size qualification. A smaller valve cannot automatically qualify every larger valve. As size increases, thermal mass changes, sealing circumference increases, structural distortion changes, body response changes, and seat loading behaves differently. Scale matters. Pressure rating matters too. A lower pressure class test cannot be casually stretched across every higher rating. Wall thickness changes, bolting changes, body geometry changes, seat forces change, thermal behavior changes. Controlled qualification rules exist because extrapolation must have limits. The same applies to non-metallic materials. A seat material substitution may look minor on a purchase order. It may not be minor in a fire. Different polymers soften, decompose, shrink, char, and retain shape differently. A changed packing material may alter stem leakage. A changed body gasket may alter external containment. A valve may still operate normally after substitution and still no longer be represented by the original fire test evidence. This is why configuration control matters from design through maintenance. A valve can leave the factory fully qualified and lose that qualification logic years later through an ordinary repair. An alternative packing set is installed, a generic gasket is used. A seat insert is replaced. An aftermarket kit is accepted because it fits. The valve passes a routine pressure test. Everyone assumes the job is complete, but routine pressure integrity does not prove equivalent fire performance. You must control the configuration that created the qualification. That is lifecycle engineering. Now look at the test itself. The valve is challenged in the closed position because the valve is being treated as an isolation barrier. One side remains pressurized. Leakage through the closure is measured. Leakage to atmosphere is measured separately. Those are not the same failure. Through-seat leakage means inventory crosses the closed valve and may continue feeding downstream equipment or a fire-exposed section. External leakage means inventory escapes directly into the surrounding environment. That can feed the fire itself. A valve can perform acceptably in one category and badly in the other. So do not review fire performance by looking only at the seat. The entire pressure boundary matters, the stem seal matters, the body joint matters, the bonnet connection matters, the cavity relief path matters. The sealing system is only as strong as the weakest pressure-containing interface. The fire exposure is controlled because qualification must be reproducible. The valve is enveloped in flame. The exposure continues for a defined burn period, but measuring flame temperature alone is not enough. A burner can produce hot flame without transferring adequate heat into the valve. That is why representative steel calorimeters are used. They confirm that the test has not merely created a hot environment somewhere near the specimen. They show that a severe thermal challenge has actually been delivered. This principle reaches beyond valve testing. Whenever you evaluate environmental qualification, separate the applied condition from the absorbed condition. One tells you what the test facility generated, the other tells you what the component actually experienced. Both are essential. Pressure is maintained during the burn and during cool down. That matters because the valve may not leak most severely at peak temperature. Different components expand and contract at different rates. The body, stem, seats, closure, bolting, packing, and gaskets do not heat uniformly. They do not cool uniformly. A leakage path that remains small while the valve is hot can open during contraction. The flames may be gone while the mechanical instability continues. That is why cooling remains part of the qualification. A fire event does not end mechanically when the burners are shut off. The same truth applies in the plant. When a fire is extinguished, the equipment may still be distorted, weakened, pressurized, and thermally unstable. Fire out does not mean equipment safe. After cooling, a low-pressure leakage test may also be required for certain valve classes. This exposes a counterintuitive failure mode. Some seats seal better at high differential pressure because the pressure helps energize the sealing system. At low pressure, that support disappears. A damaged valve may therefore appear acceptable at high pressure and leak more at low pressure. Higher pressure does not always mean worse sealing. You must understand the mechanism. Then the valve is operated after fire exposure. This is not a convenience test. It is a functional challenge. A valve may remain pressure-containing and still become seized. The stem may distort. The seat may gall. The closure may bind. Packing friction may increase. Bearings may degrade. The qualification checks whether the valve can be unseated and moved against the required differential pressure. But do not overstate what this proves. It does not prove normal operating torque. It does not prove repeated cycling. It does not prove actuator survival. It does not prove the valve can be returned to service after a real fire. It proves a defined post-fire movement under the test conditions. After that movement, external leakage is checked again because operation can disturb damaged seals. A stationary packing arrangement may remain relatively stable. Moving the stem may open a leakage path. The device must therefore remain acceptably contained after performing the required action. This is a broader safety principle. A protective device should not be judged only by whether it starts moving. It must also remain safe after it moves. Now consider body cavity pressure. This is one of the most underestimated valve risks. Double-seated valves can trap fluid inside the body cavity. When that trapped fluid is heated, pressure rises. In liquid service, the increase can be severe. The valve can be attacked by fire from the outside, while cavity overpressure attacks it from the inside. You need to know whether the valve is self-relieving. You need to know in which direction the pressure is relieved. You need to know whether an external relief arrangement is required. You need to know whether the relief feature is part of the qualified design, and you need to know what happens when both sides of the valve are isolated. Cavity management is not a minor design note. It is part of pressure boundary survival. You also need to understand what the fire test does not cover. The valve end connections are a separate integrity problem. A valve body may pass its fire qualification while the installed flange joint, gasket, bolting, weld, or threaded connection becomes the weak point. The certificate does not automatically qualify the complete installed pressure boundary. The actuator is another separate issue. The valve body may survive while the pneumatic tube melts, the hydraulic system leaks, the cable fails, the solenoid is destroyed, or the actuator seals degrade. A fire-tested valve is not automatically a fire-survivable shutdown function. Emergency shutdown performance depends on the complete chain: valve, actuator, power source, controls, cables, tubing, fail position, closure time, structural support, fire protection. System thinking is not optional. You should also stop using the words fire-tested, fire-safe, and fireproof as though they mean the same thing. They do not. A qualified valve has demonstrated performance under a defined test envelope. A real fire may last longer. A jet fire may impose more severe local heat flux. Piping may move. Structures may collapse. External loads may increase. The actuator may be destroyed. The valve may be mechanically damaged beyond the standardized scenario. Do not describe a qualified valve as indestructible. Use disciplined language. The qualification proves performance under defined conditions. Nothing more, nothing less. The biggest process safety mistake is assuming that standard compliant leakage is automatically acceptable for your system. A fire test permits defined leakage. It does not require zero leakage. That means you must translate the allowable component performance into plant consequence. Could the permitted through-seat leakage continue feeding a fire? Could external leakage materially escalate the event? Does the process require double isolation? Should the system depressurize? Should remote isolation be added? Is physical separation required? The valve standard answers whether the component passed the test. Your hazard study must answer whether that performance is enough. Never substitute component compliance for consequence analysis. This is where lead engineers must become uncomfortable on purpose. Ask why fire qualification is required. Ask what hazard it is intended to reduce. Ask what exact failure mode matters. Ask whether the supplied valve is genuinely covered. Ask whether the actuator and installation preserve the intended function. Ask who will maintain the qualification basis after handover. If nobody owns those questions, the certificate becomes decoration. Engineering managers should understand the management failure behind many compliance gaps. The problem is rarely the absence of documents. The problem is the absence of technical traceability. The project receives a certificate. Document control records it. Procurement closes the action. But nobody checks whether the tested construction matches the supplied construction. That is compliance theater. Standards exist to control physical risk. Documents exist to prove that the physical risk was controlled. When the document becomes the objective, engineering has already failed. A stronger process creates a qualification matrix. Map every purchased valve to its design family, size, pressure rating, seat material, stem seal, body seal, test valve, and qualification record. That matrix will expose the gaps immediately. One size is outside the range. One pressure class is not covered. One seat material was changed. One directional valve was never tested in the installed direction. One certificate refers to a previous design revision. That is how evidence becomes engineering control, and the control must continue after technical bid evaluation. A substitution proposed during manufacturing can affect the qualification. A gasket change can affect the qualification. A packing change can affect the qualification. A new production location can require review. The correct question is not, is the tag number unchanged? The correct question is, has the qualified design changed? Operations and maintenance teams need the same discipline. After a real fire, do not assume a valve is fit for continued service because it still operates or does not visibly leak. The body may be distorted. The stem may be damaged. Bolting may have lost strength. Packing may be degraded. Gaskets may be compromised. The actuator may have hidden damage. Fire qualification demonstrates emergency performance. It does not authorize automatic return to service. The raw truth is simple. A fire-tested valve is not a promise that nothing will fail. It is evidence that the design retains a controlled line of defense after failure has already started. That is why the test matters. And that is why your review cannot stop at the certificate. You must understand the hazard. You must understand the tested configuration. You must understand the qualification envelope. You must understand the allowed leakage. You must understand the cavity behavior. You must understand the actuator limitation. You must understand the installation. You must understand the maintenance consequences. When you see fire safe on a datasheet, pause. Ask what was tested. Ask what deteriorated. Ask what survived. Ask how leakage was measured. Ask whether your valve is genuinely represented. Ask whether your process can tolerate the permitted performance. Because standards do not remove engineering responsibility. They make engineering responsibility measurable. Share this podcast with design engineers, lead engineers, project engineers, operations teams, and maintenance professionals who still believe a certificate is the end of the review. Like the episode, subscribe to the channel, and follow my LinkedIn newsletter for more practical discussions on engineering design, project execution, technical standards, failure mechanisms, and life cycle integrity. Add your experience in the comments. Have you seen a fire test certificate that did not fully cover the supplied configuration? Have you dealt with uncontrolled seat, packing, or gasket substitutions? Do you believe fire-tested valve requirements are being engineered through consequence, or simply copied from previous projects? Your observations, disagreements, and field lessons matter because the strongest engineering guidance is often built from the gaps that formal documents never expose.